Hello students, now we will go for another chapter of your syllabus phenyl propanoids and flavonoids of B.pharmacy 5th sem in the pharmacognosy and phytochemistry. You know phenyl propanoids. Phenyl propanoids are having C6, C3 units, and this category phenyl propanoids are a diverse family of organic compounds that are synthesized by the plants from amino acids phenylalanine and tyrosine. Yeah. This group phenyl propanoids, this also known as cinnamic acid, are relatively simple secondary metabolites that are derived from cyclic acid pathway. So we will discuss all the phenyl propanoids under this category. Lignans are coming, so we will discuss first of all, and lignans and flavonoids is the name of your chapter, and we will discuss first flavonoids. What are flavonoids? Flavonoids are low molecular weight polyphenolic substances that, based on the flavon nucleus, it occurs in free form as well as in glycosidic form. So glycosidic form, you know, the glucose moiety or glycogen is present. So there is glycosidic linkage that also we will discuss in the glycosides. But there are examples for phenyl propanoid derivatives that are already we discussed, C6 and C3 derivatives, and you know this is the structure, basically generic structure of flavonoids, and our numbering system used to distinguish the carbon positions around the. So flavonoid structure, the three rings A and B is chromine, benzene fused with a pyran, and C, and another C ring is phenyl. So next point, six-membered ring condensed with the benzene ring is either a pyran or its dihydro derivative. Then when glycosides of flavonoids are formed, the glycosidic linkage is normally located in position 3 or 7, and the carbohydrate can be levorotatory, L-rhamnose, and D-glucose, and glucorhamnose, galactose, or arabinose, for example, rutin O glucoside. Yani this is a O glycoside, yani linked with the oxygen. Then camphorol O glucoside. Then flavonoid glycosides a glycon, non-sugar part plus glycon sugar part. We are well aware about the glycosides. This is composed of two molecules. One is the sugar part and another is non-sugar part. When glycosides are formed, the glycosidic linkage can be located in the position 3 or 7 and may be L-rhamnose, D-glucose, galactose, or arabinose. So these are the exoses which are mentioned for the glycosidic linkage. Then you can see the structure of flavon glycoside, flavonol, and flavon, isoflavon, flavan, 3-ol, and flavonol, and anthocyanidin. So you can see the structure, how it is mentioned. Then classification. They are classified according to the chemical structure into number 1, flavons. Flavons, number 2, phenylchromine 4,1, number 1, apigenin, luteolin, then tangeritin, then diasmatin. These are the then flavonol, 3-hydroxy 2-phenyl Chromium 4,1. Then example, camphorol, rutin, myristicin, quercetin, quercetin, and then ficetine. So this is basic structure given. Now flavonon, 2,3-dihydro 2-phenyl chromophene, chromine 4,1,4,1. The example of these phenomenons are naringenin, hesperidine, and naringenin and butene. These are the examples of flavonon. Then flavonol, flavonol. The details are 3-hydroxy, 2,3-dihydro, 2-phenyl chromine, 4,1, 4 on, O and E on. This is 1, O and E on. So example, taxifolin, silymarin, then taxifolin. This is the structure. Again, next is flavon, 3-ol, known as flavonol. Flavonol is the alcoholic group. Then alls are all alcohol. So catechin, B hydroxide. So in the bracket, B hydroxyl group, beta hydroxyl group, and then structure is like this. Then second is epicatechin. This is having the linkage with the alpha hydroxyl group. Then isoflavons. Isoflavons, 3-phenyl chromane, 4 on, O and E on. So under this isoflavon, the numbering is made in the benzene rings, different benzene rings like this, and then isoflavon are categorized into genistenin, then dadgin. So at the position of 3 position there is nothing attached. Then at 5th position, if hydroxyl group, OH group is there for genistein, and 7th position also hydroxyl group, and 4' position also hydroxyl group. Then dadgin at position 5 there will be hydrogen linkage, then 7 O glucose linkage, and then at 4' there will be hydroxyl group. So this is dadgin structure. Then anthocyanidins, flavinium, that is 2-phenyl chrominylium ion skeleton of anthocyanidins. So this is the structure, and you can draw the structure of cyanidine. Cyanidine is the structure, and then another is delphenidine. Delphenidine is also coming under anthocyanidins. Then pharmacological action. These flavonoids are having antioxidant properties, and they are anti-inflammatory in nature, and this anti-ulcer properties are also there, and then it is used for anti-rheumatic problems, and it is a hepatoprotective. For example, silymarin can be given in hepatoprotective as a hepatoprotective, because in the liver problems we can give this, and anti herociliosis, anti-herociliosis, and anti-cancer. These are the pharmacological. Then identification and characterization. For identification, what are the different chemical tests? You can see tests for identification. The different types of flavonoids can be characterized by their colored response to different tests visible in the visible light, which we can see with the naked eye, or colored fluorescence in UV light, ultraviolet light. There are two types of light: visible light, which we can see with the naked eyes, and another is fluorescent in UV light. The number one, reaction with aluminum aluminum chloride. The different classes of flavonoids gives yellow color with aluminum chloride. Then, but fluorescence is differently in UV as shown in the following table. Light, flavonoids, flavonons, the different visible light or UV light. So for different categories, flavons, flavonols and flavonons, these are having different. If the ketonic group is there, that will come under flavonons, and then flavons. Flavons are having the different category, and with the flavonons is having hydroxyl group. So in visible light, flavons will behave and give the yellow color. Then again, all the three will give yellow color in the visible light. But under UV light, if you will see flavons, it will give green color, and flavonols yellowish to yellowish green. Then flavonons yellow, this pale to brownish. So these are the identification or rather characterization property. Then next is lead substrate test. All flavonoids give yellowish precipitate with lead substrate. Then Synoda test for flavonons and flavonols. Alcoholic solution plus magnesium metal or slash with hydrochloric acid, and orange or red or violet color is produced. So then next, 4 antimony pentachloride test for chalcones. So chalcones, alcoholic solution plus uh, this HbCl5, यानी antimony pentachloride HbCl5, and then CCl4 carbon tetrachloride, then it will give red or violet color is produced. Then biosynthesis. Already we discussed in the beginning that plant proteins are biosynthesized through cyclic acid pathways or amino acids using the pathway of phenyl, aniline or tyrosine. Then precursor, that is 3 molecules of acetic acid and phenyl propane moiety. Phenyl propane moiety, yani C6H3 moiety is involved. Then interaction of different pathways, then interaction with the different pathways, phosphanol pyruvate pentose phosphate pathway to get erythrose 4-phosphate, and cyclic acid pathway, aromatic biosynthesis. Already we discussed in the cyclic acid pathway, both are the different steps. When the carbohydrate will split into pentose phosphate pathway, it will go in the another. Then the pentose phosphate will change to erythrose 4-phosphate, that is tetrosis. From pentosis it will change to tetrosis. First hexosis, it will change to pentosis, and pentosis to tetrosis, and tetrosis it will go, there will be formation of cyclic acid. It will go in the aromatic biosynthesis of all compounds, secondary metabolites, and then for pyruvic acid and pyruvate formation, it will go for the formation of terpenoids. We have seen aromatic terpenoids, isopyrenide units are there, and that will be this aromatic biosynthesis, the formation of terpenoids, and by the cyclic acid pathway we will get the another secondary metabolites. We have already discussed all this in detail in the biosynthetic pathways. The general Phenyl propanoid metabolite that produces activated cinnamic acid derivatives, and also the plant structural component lignin, and finally the diverse specific flavonoid pathway. So already, if you will, you can recall, we have through the shikmic acid pathway, we are getting lignans and lignins, and then flavonoids also formed through the shikmic acid pathway and mevalonic acid pathway. Mevalonic acid pathway will come from the uh, pyruvate and pyruvate phosphate. It will change to mevalonic acid, and mevalonic acid will change for the terpenoids and flavonoids. But through the shikmic acid pathway, we will get phenyl propanoid unit, C6H3, and it will give all this lignans formation will be there. Then biosynthesis is cinnamic acid derivative phenylpropane synthesized from citric acid acts as starting compound in a polypeptide synthesis. If you remember, all these details we have discussed in the biosynthesis, in which an additional 3 acetate residue are incorporated into the structure, and this is followed by the ring closure. So already we have had a discussion in detail in our biosynthetic pathways, and through subsequent hydroxylation and reduction by using the different enzymes, the plant then able to biosynthesize different classes of flavonoids like flavanol, flavons, flavonans, catechins, and all polyphenolic compounds. All polyphenolic compounds like tannins and anthocyanins, isoflavons, dihydroflavons, and chalcones, and even tannins. All these polyphenolic compounds are formed through this subsequent hydroxylation and reduction by using different steps and of involving different enzymes. So this is the phenyl propane. You see, this is the structure from where we will get the cinnamic acid, acetic acid, and this is split into acetic acid, flying propane, and then polyketide. This is the structure. Chalcone moiety. This is flavonoid moiety. Flavonoid for the formation of flavonoids, and from chalcone moiety there will be formation of flavonoids. So this you can see shikmate pathway. Shikmate pathway already we have discussed. Cinnamic acid, phenyl, aniline, tyrosine, and this transcinnamic acid, and all this will lead to melanine CoA and melanine CoA 2. This will go into fatty acid chain for the formation of long chain fatty acids. But another thing that will be malonate pathway. But we have discussed malonic acid pathway, malonate pathway. Malonate pathway is for formation of long chain fatty acids, but malonic acid pathway for the flavons, isoflavon, flavonons, and all the flavonoids are formed through this. But another pathway, cyclic acid pathway, we will get the lignans, formation of lignans, and flavonoids are formed from the this chalcones, and it will come from the mevalonic acid and mevalonate CoA, melanine CoA. So these are the different steps for formation of all these compounds. Then lignans. Lignans are subgroup of non-flavonoid polyphenols. Understand? Subgroup of non-flavonoid polyphenols do not occur in free form but occur in glycosidic form. It is having glycosidic form, yani the glycosidic linkage involving O glycoside, C glycoside, and different where the N glycosides, where the linkage is through nitrogen, then N glycoside. If the linkage is through carbon, then C glycoside. If the linkage is through or oxygen, O molecule, then O glycoside. They are widely distributed in the plant kingdom, being present in more than 55 plant families, where they act as antioxidant and defense molecule against pathogenic fungi and bacteria. So, podophyllatoxin is the example of lignans, and we get the podophyllatoxin from obtained from the plant of genus Podophyllum, Phyllatum, and Podophyllum Hexandrum Barbaridaceae. Barbaridaceae is the family, and it is a mitotic toxin whose derivative has been used as chemotherapeutic agent, anti-cancer agent, and arctigenin and tracheologan antiviral obtained from the tropical climbing plants. Then linseed flax seeds contain sequoisoleryresinol and leryresinol. These are different phenolic compounds containing this phenolic group, or then pinoresinol and meteresinol. These are the different examples. The chemical structure: two phenylpropane unit linked by C carbon between the central atoms of the respective side chain. You see, these are the details of how the linkage is formed, and hence their chemical structure is referred as C6C3. So two units are there, three units are also there for cyanidine and other lignans. There are two units of phenylpropanoid units, or more than that also is there, and they are included as phenylpropanoid group as well as their precursors hydroxycinnamic acid. Cinnamic acid, as you know, is a phenylpropanoid, this unit. Then following structure contains phenylpropanoids and B lignan. You see, A and B. A is the you see, this is the structure of phenylpropanoid, yani phenyl group, and then 3 carbon C6C3. C6C3 C3 is the C6 comes from the benzene ring phenyl group, and 3 carbon molecule from 1, 7, 8 and 9. These are the 3 carbon molecules. So it is called C6, C3 units also. It's another name. In chemically we can call it like that. And then B structure is also there. That is the lignan structure. Then biosynthesis of lignans. These are the details. The pathway starts from 3 of the 4 most common dietary hydroxycinnamic acid and para-cumaric acid, cinnabic acid, and ferulic acid. This ferulic acid from caffeic acid is not a precursor of this subgroup of phenyl polyphenols. Therefore, they arise from sigmic acid pathway via phenylalanine. The first 3 reactions reduce the carboxylic acid of the hydroxycinnamates to alcoholic group, and with the formation of corresponding alcohol called monolignols. That is para-cumaric alcohol and synapyl alcohol and coniferyl alcohol. These molecules also enter the pathway of lignin biosynthesis. The first step, so these are the details, first step, and the second step, what are the enzymes and coenzymes, and then there will be, these are the details. And the next step, the dimerization of monolignones involves the intervention of the stereoselective mechanism, or more precisely enantiomeric selection mechanism. Plant lignans exist in the what's the dextrorotatory or levorotatory enantiomers. As dextrorotatory is plus, if the we will write in the plus form, and in the like minus dash, it is stands for levorotatory. And these are the different dextrorotatory and levorotatory enantiomers. Yani, their structure is same, but their chiral chemistry differs by dextrorotation and levorotation. So these are the different steps for the formation of lignans, how it is biosynthesized. You can see the different steps. In fact, most of the plant lignans exist in dextrorotatory or levorotatory enantiomers, whose relative amounts can vary from species to species, but also in different organs on the same plant, depending on the type of reaction involved. And the dimerization can occur through enzymatic reaction involving lacases. These enzymes catalyze the formation of radicals that dimerizing form a racemic mixture. You know, the racemic mixture is the mixture where the both dextrorotatory and levorotatory enantiomers are present. So, Phenyl is not in your syllabus. We'll finish the phenyl propanoids and flavonoids. Thank you.